In Chapter 4 we dealt with the structure of the atom. We talked about the protons and neutrons being in the nucleus and the electrons flying around the nucleus, and how every element had a unique number of protons inside of it. That protons and electrons equaled each other to make a neutral atom. Well, now we're going to start putting the atoms together to make compounds, and I have this beautiful picture. I assume this is in Alaska or Glacier National Park, and it emphasizes this important idea, and I like the way our text states this on page 128. This is the great wonder of nature, how from such simplicity, protons, neutrons, and electrons, we get such great complexity. It is exactly this complexity that makes life possible. Life could not exist with just 91 different elements if they did not combine to form compounds. It takes compounds in all of their diversity to make living organisms. So that's what we're focusing on with this chapter, is naming and writing formulas for different compounds. It's an amazing idea that you can take sodium metal, which is a really reactive metal, it will explode in water, mix it with chlorine gas, which is toxic to you, and you get salt, which we put on our food all the time. So compounds are completely different than the elements that compose them. Another idea, which is expressed in section 5.2, is that there's a really consistent ratio of the elements inside of the compound. So all carbon dioxide has 2 oxygens with 1 carbon, comprises dry ice, which we played with just last week. Carbon monoxide is distinct from carbon dioxide. It has 1 oxygen on 1 carbon, and that's also toxic to you if you'd inhale that. So I'm showing you chemical formulas. It's a really concise way of saying a lot of things. Water has 2 hydrogens with an oxygen, H2O. You've known that formula for a while. Once you know your element symbols, you're capable of writing that. C12H22O11 you'll probably remember from biology. That's sucrose. We have 12 carbons, 22 hydrogens, and 11 oxygen atoms in 1 sucrose molecule. How many atoms of each type are in aluminum sulfate? Here's the formula for aluminum sulfate. Well, I hope you said 2 aluminums, 3 sulfates, and 12 oxygens. When you have parentheses like this, you multiply everything inside of it by that number. There are other kinds of formulas. This CH4, that's called the molecular formula. It shows all the elements and their ratio. Structural formulas contain more information. They actually show the bonds that are between the atom. The ball and stick model gives a little 3-dimensional aspect, as does the space-filling model. Before we get into writing formulas, let's review the periodic table a little bit. We have the staircase that runs through here, and the stairs separate the metals from the nonmetals. The metals all become cations, and the nonmetals tend to become anions. When we're making compounds, we need to take into account whether the compound ionically bonds, as in setting up these charges and transferring electrons, or if they covalently bond, which is sharing of electrons. We name them differently depending on which type of bond forms. There's a general protocol that we usually put the element in the front that is most metal-like, or the one that is more on the left of the periodic table. So if I was trying to write a formula to put 2 silver atoms with 1 sulfur atom, silver comes before sulfur on the table. Here's my silver, and here's my sulfur. So I would write Ag subscript 2S is silver sulfide. If I had to write the formula for 2 nitrogen combining with 1 oxygen, these are both nonmetals over to the right of the stairs, but the nitrogen is to the left of the oxygen, so it goes first. Dinitrogen oxide, you will learn the name of that. And then finally, if you were to combine 2 oxygens with 1 titanium, titanium is here. Oxygen's over there, so titanium goes first. It's the metal. 2 oxygen with 1 titanium. That's titanium 4 oxide. Again, this nomenclature is what we're working on with this chapter. Let's organize this a bit. To have a pure substance, it could either be a pure element or it could be a pure compound. Elements appear in 2 different forms. There are individual atoms. Noble gases such as neon do this. The elements that form diatomic molecules are hydrogen, nitrogen, oxygen, and all of the column 7 elements. You need to memorize this because they can appear in chemical reactions and you need to know to write them as a diatomic molecule. This is showing elemental mercury and this is showing elemental chlorine. Alright, let's look at compounds. Compounds may be either molecular, when they share electrons, or ionic, when the electrons are transferred. Now moving into ionic compounds and how we write them and name them. What is an ionic compound? We're saying an ionic compound is when a metal combines with a nonmetal, the metal transfers its electron to the nonmetal. The fundamental building block of an ionic compound is called a formula unit. This is all in contrast to a covalent compound, which is when 2 nonmetals are bonded to each other. They share electrons, and that is the official definition of what a molecule is. 2 nonmetals sharing electrons. Finally, it's possible to have metallic bonds. This is when you have 2 metal atoms together. There's something called the electron sea, and I'll show you an animation of that. Metals are very deficient in outer shell electrons, and they have so few that the electrons flow over them all, making the metal very conductive. We don't have a special name for the subunit of a metal. It's a lot of different metal atoms side by side with the electrons flowing over them, such as this. Okay, all the little red pluses are indicating the nuclei centers. The blue moving electrons are trying to satisfy all those positive nuclei. There's a real shortage of electrons in metals, and they are delocalized in a sea. We call it the electron sea. We're now going to focus on the ionic compounds. That's when the metal gives its electrons to the nonmetal, and as a result we have a metallic cation and a nonmetal anion. When we're writing formulas for ionic compounds, we need to make when we're writing formulas for ionic compounds, we need to make it electrically neutral. Electrons will transfer from the metal to the nonmetal. We can't have fractional electrons. It has to be a whole number exchange. So we make the charges equal, the positives and negatives. There are certain ways to know the charge on the metal ion. There are certain ways to know the charge on the metal ions. Things that are certain are all column 1 metals prefer to be +1, and all column 2 metals prefer to be +2. It makes them more stable. It's also true that column 3 metals prefer to be +3. Those are the only reliable metals. On the nonmetal side, it's reliable that column 7 elements prefer to be -1, and oxygen consistently prefers to be -2. Other than that, you have elements that are medium in their willingness to transfer or gain electrons, and it will depend on the atoms that they're bonded to. To make the charges equalize, we end up with this crisscross method that's shown here. Aluminum is a column 3 metal, and so it adopts a 3+ charge. Oxygen is very stable with a 2- charge. Well, these don't add up. The 3+, 2- are uneven. So with a crisscross method, we have in effect a 6-electron move. Okay, 6 electrons. Exchange. Well, let's look at magnesium with oxygen. Magnesium is a column 2 metal, so it adopts a 2+ charge. Oxygen, again, is very stable as a 2-, and so these match 1 to 1. I would write this MgO. The 2+, 2- go together perfectly. It's a 1-to-1 relationship. It's a 2-electron move. We've taken care of ionic compounds in which the metal forms only one type of ion. There are some other metal ions that we have to deal with that are variable in their charges. These are the transition metals, and I'm just putting up here a chart that shows their favorite charges that they adopt. What we do to handle this is use a Roman numeral system to give the charge. So chromium can be either 2+ or 3+. Chromium can be either 2+ or 3+, so we call it chromium Roman numeral 2 or chromium Roman numeral 3. We need to specify the charges for metal ions that are transition. We need to specify the charges for transition metal ions. On the nonmetal side, you can see that the halogens adopt a -1 charge readily. Oxygen adopts a -2. Sitting right underneath oxygen in column 6 is a sulfur, which is often 2-. And in column 5, you'll find nitrogen, which will likely adopt a 3-. Later on in chapter 9, we talk about the octet stability. And really what we're doing is seeing these atoms fill their outer shell with 8 electrons, and that makes them more stable. Let's get to naming these compounds. If we had copper, it can be copper 1 or copper 2, depending on if it's the +1 or the +2. If we were to write the formula for copper 1 oxide, we would write it with a copper 1 combining with an O2-. This is not even, and so crisscross, I would need 2 coppers to balance the 1 oxygen. Copper 2 oxide means copper 2+ with O2-. These guys are a perfect pair, 2+, 2-. CuO is copper 2 oxide. Notice the general naming convention, the name of the cation, copper, the charge in Roman numerals, and then the anion's ending gets changed to IDE. So I say oxide, I don't say oxygen. There's another kind of ion that you need to brute memorize. They're the polyatomic ions. They're very common. You'll recognize the names. But you're going to have to memorize their structure and their charge. For instance, you've heard of nitrates before. It's important for agriculture to have nitrates present in the soil. Nitrate is nitrogen with 3 oxygen and an overall -1 charge. Nitrate is a very stable polyatomic ion. You'll see things such as magnesium nitrate form. This contains 1 magnesium, 2 nitrogens, and 6 oxygens. It breaks apart into magnesium ion and 2 nitrates. The nitrogen does not break apart from the oxygens under normal circumstances. These are the polyatomic ions that you need to memorize. It's an intimidating list. It's one of the hardest things I ask you to do all year. I have a few helpful hints for you. One is focus on the ATEs, the nitrates, sulfate, phosphate, carbonate. If you memorize those, then you can convert to the nitrite, the ITEs, by taking away an oxygen and not changing anything else. Notice how the sulfite is O3 versus O4, otherwise it's the same. Another memorization helpful hint I'll give you another helpful memorization tool are the CHLORATE series. If you would memorize just CHLORATE and its structure, you can figure chlorite is 1 less oxygen. Then teach yourself that hypo means take 1 more oxygen off, so we peel away another oxygen to be ClO minus. Then also train yourself that perchlorate means 1 extra oxygen, so you get ClO4 minus is perchlorate. Well, if you can memorize this, base of chlorate, -1 is chlorite, -2 is hypochlorite, +1 is perchlorate, then you've also memorized the bromate series and the iodate series. They're all the same. Learn the pattern. You see these polyatomic ions in things like bleach, which is sodium hypochlorite, baking soda, which is sodium bicarbonate. Calcium carbonate is the active ingredient in Tums, and sodium nitrate is a food additive in meats. I'd now like to look at a few sample problems. I'd now like to look at a few sample problems and try to apply some of this. What do you think the name of this might be? You see an iron element, sulfur element. What's this 2,3 bit? That's reverse crisscross. This is iron, 3. How do I handle just a sulfur? Well, the rule is start saying sulfur but change it to ide. This is iron 3 sulfide. What would you name this compound? Well, you don't know your polyatomic ions yet, but this is that immediate association you'll eventually make that is sulfate. So you just say sulfate. Whenever you see the polyatomic ion, just say it. Now a sulfate, you will memorize, is a 2- polyatomic. That means this must be Fe2+ because it's going 1-to-1 with the sulfate. So this is iron 2 sulfate. Let's name this. Here's iron. Do you know the name of this polyatomic ion yet? It's a little early for you to know that. But reverse crisscross, there's an understood 1 here. It's a -1. This is a 3+. Iron 3. Have you figured it out? Perchlorate. It's got the 4 oxygens on it. It's the perchlorate. How about PbCO3? Again, polyatomic ion is what you should be saying to yourself. Carbonate has a 2- charge. So this must be lead 2 carbonate. I have 2 worksheets that you'll work on, and drill and practice is the way to learn these.